let's go through some definitions. Let's see who remembers these definitions from elementary school. A blank triangle is a triangle in which no two sides are congruent. Bridget. Scalene, good. And blank triangle is a triangle in which all sides are congruent. What's a triangle with all sides congruent called? Can wait, somebody knows. Somebody said, what do we call all sides congruent? Milo? Isosceles has two sides. That'll be coming up soon. So we're close. We're getting closer. Noah? Equilateral. You got it. An equilateral triangle. Okay, that word equilateral can be applied to any figure with all sides congruent. So if you have a pentagon with all sides congruent, it's an equilateral pentagon. If you have a hexagon with all sides congruent, it's an equilateral hexagon. Equilateral means all sides congruent, right? All right, now we're going to put a twist on the isosceles definition. An isosceles triangle is a triangle in which at least two sides are congruent. I think the definition you knew before was an isosceles triangle is a triangle with exactly two sides congruent. So now it's upgraded a little bit. Now it's at least two sides congruent. What does that mean if it's at least two sides congruent? Aaron? It could have two or more sides congruent. So here's an always, sometimes, never for you. Always, sometimes, or never. An isosceles triangle is equilateral. Remember, equilateral means all sides congruent. An isosceles triangle is equilateral. Let's do a vote. How many people say an isosceles triangle is always equilateral? An isosceles triangle is sometimes equilateral. An isosceles triangle is never equilateral. Good, you all win. An isosceles triangle is sometimes equilateral. Let's flip it. An equilateral triangle is isosceles. An equilateral triangle is isosceles. How many people say an equilateral triangle is always isosceles? An equilateral triangle is sometimes isosceles. An equilateral triangle is never isosceles. Okay, how many people said an equilateral triangle is always isosceles? Well, I'm only going to give credit to like the first three people that put their hands up because I think everybody else just sort of looked around then added their hands, but it is. An isosceles triangle is always, an equilateral triangle is always isosceles. Why? Definition of isosceles, at least two sides congruent. Isn't that the definition? Does an equilateral triangle have at least two sides congruent? Yeah, it has three sides congruent. So an equilateral triangle will always be considered isosceles. Now, for the purpose of geometry, when we say an isosceles triangle, we are going to the most precise definition of isosceles, which is two sides congruent. And anytime we have two sides congruent, the two sides that are congruent have names. They are called the legs. So in the first triangle here, side AB is a leg, segment BC is a leg. And the side that's not congruent is called the base. So AB is a leg, BC is a leg, the side that's not congruent is the base. So let's label this out. Our legs are segments AB and BC. Our base is segment AC. Now, where do you think the base angles are? Adam? You got it. The base angles will be on the base. So once you identify the base, you can then identify the base angles. The base angles are always on the base. So angle A and angle C are considered the base angles. The vertex angle is the angle that's not the base angles. It's also the angle formed by where the two legs meet. Chase.
Angle B.
Angle B, you got it. All right, you all identify the sides of this next isosceles triangles, the legs, the base angles, and the vertex. And then we'll go over it. All right, who can identify the legs for me? Olivia. You got it. Segment DE and segment EF. Can someone identify the base segment for me? James. DF. You got it. The base angles. Aaron. You got it. And the vertex angle, Connor.
Angle E.
You got it. All right, let's keep going. Another definition, a blank triangle is a triangle which all angles are congruent. This is an equiangular triangle. Equiangular. Let's talk about an equiangular triangle. In a triangle, if you add up all the interior angles, what is the sum of all the interior angles in a triangle? Adam. 180. All interior angles have a sum of 180. Always. If you always add up all the interior angles in a triangle, it has a sum of 180 degrees. Now, if it's equiangular, doesn't equiangular mean all the interior angles are congruent? So how would we find just one interior angle if it's equiangular? You got it. So 180 divided by 3, we get 60 degrees. So if a triangle is equiangular, do we agree every angle has to be 60 degrees? All right, more definitions. A blank triangle is a triangle in which all angles are acute. Bridget? An acute triangle. Right? Nice and small and cute. All the angles. They're all less than 90 degrees. Right? A right triangle, the next definition is a right triangle is a triangle in which one of the angles is a right angle. Can we ever have more than one right angle in a triangle? Is it possible to have two right angles in a triangle? Why not? Why is that impossible to have two right angles in a triangle? Mariana?
Because then it equals 180.
Good, because then just two angles together add up to 180. Is that what we want for a triangle? No, you need all three angles together to equal 180. Right, so now when we have a right triangle, there's special names for the sides of the right triangle also. The side that's across from the right angle, the longest side of the triangle across from the right angle. Milo? Yes, it is the hypotenuse. So the side across from the right angle is the hypotenuse. The other two sides are called the legs. Now the legs in a right triangle differ from the legs in an isosceles triangle. What do we know about the legs in an isosceles triangle? What do we know? What do we know about the legs in an isosceles triangle? They have to be what? Chase? Congruent. In an isosceles triangle, they have to be congruent. They do not have to be congruent in a right triangle. Could they be congruent? Sure. Do they have to be congruent? No. All right, the side opposite the right angle is called the hypotenuse. The sides that form the right angle are called legs. And our last definition for today, an obtuse triangle. An obtuse triangle is a triangle in which one of the angles is an obtuse angle. Right, we're going to skip sample problem number 1. We don't do any paragraph proofs. All our proofs will be 2-column proofs, so we don't need to worry about number 1. Let's go on to number 2. Let's go on to number 2. Right, here we have angle 1 is congruent to angle 3. We have angle 2 is congruent to angle 4. And we have, oh, the P is missing. The P should be this point right here. Segment JP is congruent to segment PO. We need to prove that triangle KPM. Hello. Oh,
I know you
thank
always
you.
want to.
Oh my goodness, this is great. Thank you. All right, we want to prove that segment KPM is isosceles, so we need to prove that this triangle is isosceles. How do we prove a triangle is isosceles? We have to show two sides congruent. Do we all agree? We need to show two sides congruent. As of right now, there's no reason we can say two sides are congruent. So we're going to prove triangles congruent. Don't do this. I'm going to show you. I think my first instincts would have been for these two triangles to prove congruent. And not a bad idea, considering we have a side, and don't we have an angle? Can we do vertical angles? If we do vertical angles, wouldn't that be angle, angle, side? At this point in the year, are we allowed to use angle, angle, side? No, at this point, we are not allowed to use angle, angle, side. Do angles 2 and 4 count towards those green triangles? No. So will the green triangles work? No, the green triangles are not going to work. Do we force it? No. We have to find another pair of triangles that we could potentially get to be congruent. We need to find another pair of triangles that we can potentially get to be congruent. Does anybody see? It's not going to be a direct CPCTC. It's going to have to go a little bit long way around. Erin, what do you see? Perfect. I see the overlapping triangles also. So triangle OKM and triangle JKM. All right, so now I'm going to go through my given again and see what works for us. Angle 1, right here. I'm looking at the overlapping triangles. Is angle 1 a full angle in any of the triangles that we're trying to prove congruent? No. Angle 1 and angle 3 are not full angles. Let's keep going. Angle 2. Look in the red triangle. Is angle 2 a full angle in the red triangle? It is. Angle 2 is absolutely a full angle in the red triangle. It's right over here by K. What about angle 4? Look at the blue triangle. Trace the blue triangle, look at it. Is angle 4 a full angle in the blue triangle? Yes. So that absolutely counts as an angle for us. So we have angle 2, we have angle 4. Does anybody see, you got to use the overlapping triangles, in the blue triangle and in the red triangle, how I can get the big angle K congruent to the big angle M? Looking at our markings, how can I get the big angle by K congruent to the big angle by M? Olivia? Addition, you got it. So that's going to be my second step right here. I'm going to say I got to name it with 3 letters. So angle, not triangle, angle JKM is congruent to angle OMK addition. So that gives us the big angle by K congruent to the big angle by M. So now we have 2 angles. Does anybody see anything else we can say to get these triangles congruent? What else? Okay, Chase.
Segment KM is congruent to itself.
You got it.
Reflexive.
KM congruent to KM reflexive. All right, so now I can say triangle JKM. So I said triangle JKM. How are we going to match it up? Adam. OMK, you got it. And that is angle, side angle. So remember, our end game here is to get KP and MP congruent. Can I CPCTC KP and MP? Adam, you're shaking your head no, and I love it. Why?
Because it's not a full side of the triangle.
Good. You could only CPCTC full sides or full angles. We cannot CPCTC KP or MP. But is there a full side that has KP and MP in it that could potentially help us out here that we can CPCTC? Yeah, I can CPCTC JM and OK. So let's do that and then talk about why this helps us. All right, so now that we got the full JM congruent to the full OK, and weren't we told in the beginning that JP and OP are congruent? So now since the top portions are congruent and the full segments are congruent, can I subtract those top JP and OP to be left with KP and MP? That's what we want to do. So now I'm going to be able to say that JP is congruent to OP subtraction. I'm running out of space here. And then our very last step is going to be, now that we got those 2 sides congruent, I'm going to say triangle KPM is isosceles, and your reason will just be def of isosceles. We showed 2 sides congruent. That is the definition of isosceles. Can we move on to the next one? Okay. Anybody still copying? Because I'm going to have to erase. Sure. Like, how far up? Like, right here?
Yep.
Okay. We good, Connor? All right, let's go to the next one. right, so here we are told that AD and CD are legs of an isosceles triangle. This is really important. Anytime we have given that we have an isosceles triangle, something extra has to also be told to us. It can't just say it's an isosceles triangle. It has to either tell us the base or the legs or the vertex angle or the base angles. Why? Because if they don't give us some extra information, there's 3 sides in the triangle. Would we know which 2 have to be congruent? No. So when they say AD and CD are the legs of the isosceles triangle, doesn't that mean to us that we now know in an isosceles triangle it's the legs that are congruent? So that's where we're going to start first. That's our first conclusion that we're making. Since AD and CD are the legs of an isosceles triangle, I can conclude that AD is congruent to CD, and your reason is just def of isosceles. We know the definition of isosceles is 2 sides are congruent, so we are using that. Those are going to be the 2 sides that are congruent since they are the legs. Then it tells us that B is the midpoint of segment AC. If B is the midpoint, what can we conclude? Adam.
Segment AB and segment BC are congruent.
You got it. Segment AB is congruent to segment CB. It doesn't matter. CB, BC, all the same.
Yeah.
And that is what reason, Adam?
Def of midpoint.
You got it. Def of midpoint. All right, as of right now, we went through our given. We've made as many conclusions as possible. Let's see what we want to prove. We need to prove that angle A is congruent to angle C. As of right now, can we prove angle A congruent to angle C? No. Right, so what is our plan? Every time we can't prove what we want from the given information, to prove what? Triangles congruent. What's the problem here? There's only one triangle. Anybody see how we can fix that problem of only having one triangle? So? You got it. We can draw our segment from D to B. And in our proof for this step, we're going to write draw segment DB. And remember, I told you I wasn't going to take any variation of this postulate. So you tell me, what is it? Connor.
2 points determine the segment.
You got it. 2 points determine a segment. Well, now we have 2 triangles, and don't we already have 2 sides congruent? Anybody see where we can get our last piece to get these triangles congruent? Milo. You got it. DB congruent to DB reflexive. And now the triangles are congruent by what method? SSS. You got it. So triangle ADB. So I said ADB. Who's going to match it up for me? So if I say ADB, what's the other one going to be? Colin, what's the other one going to be? I said ADB. You got it. CDB. And that's side, 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 SSS. And now can I say angles A and C are congruent? Yes, by what reason? What reason? Someone new. Caleb, what reason? You got it. All right, you all do your independent, and then we will go over it. Let me see.